Hey everyone, as you can guess, this video is about calculating Kc from concentration data. And in this problem we're going to learn how to use what's called a Rice table to help solve these types of problems. In this particular case it'll be pretty easy and one might be able to see why you wouldn't even need a Rice table. But as we get more complex and these problems get harder and harder, you'll be happy we do it this way. This question says, in order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.20 moles of HI gas, hydrogen iodide gas, and allow the reaction to proceed at 453 degrees Celsius. At equilibrium, the HI concentration equals 0.078 molar. Calculate Kc. So in this case, what we do is we set up a Rice table, and Rice stands for reaction, initial, change, and equilibrium. So the R is simply the balanced chemical reaction, which I'm just going to rewrite like this. And I stands for the initial concentration. And we do see here that there's 0.20 moles in 2 liters. And concentration, of course, is moles per liter. So the initial concentration is 0.200 moles per 2.00 liter. And as the problem tells us, there is 0 moles of the H2 and 0 moles of the I2 to start. We only start with the HI. Now the change in this case is minus for the HI because of course we're only going to lose HI. And because there is a 2 in front of the HI, it's minus 2x. X meaning an amount that we're going to figure out. And because the H2 has a 1 in front of the balance and 1 in front of it for a coefficient, and the HI also has a 1, we simply add x of this and x of this. And of course these are positive x's because starting out with 0 concentration, those concentrations are going to grow. And because of the 2 in front of the HI, its concentration is going to decrease twice as fast as the H2 and the I2 concentrations are increasing. So we take account for that with the minus 2x. And we can easily see that, let's see, right, 0.2 divided by 2 here, that simplifies to 0.100 molar. So 0.100 molar minus 2x at equilibrium. And at equilibrium, this is 0 plus x, which is just 0. And this is 0 plus x, which is just 0. This line right here that I drew sort of is the summation. At equilibrium, where are these concentrations going to be? So I can take this a little bit farther. I do know something about equilibrium concentrations right here. The HI I know is 0.078 molar. And this right here is my expression for what the HI is doing at equilibrium. So I can use this to solve for x. So at equilibrium, right, HI's concentration is 0.078 molar, and that's equal to this right here, 0.100 minus 2x. So from this, I can just rearrange and actually solve for x. X is equal to 0.011 molar when I rearrange. So what that tells me is that at equilibrium, the HI concentration, which we knew from the beginning, right, was 0.078 molar. The H2 concentration, because it grows by x, is now 0.011 molar. and the I2 concentration is also 0.011 molar. If I look up in the top, I believe it also asks me to calculate Kc. I do have these concentrations now, and according to the balanced chemical equation, Kc is going to be H2's concentration times H2's concentration times I2's concentration divided by HI's concentration squared. As I look back up, there was the 2 in front of the HI, so that concentration is squared. So therefore, K's value is 0.011, because this is 0.011 and the H2 and the I2 concentrations are both 0.011. It's 0.011 squared divided by 0.078, and that also is squared. That leaves us with a Kc of 0.020. So just to review really quickly, we set up what's called a Rice table when we're solving these types of equilibrium problems. R stands for reaction, I stands for initial concentrations, C stands for the change, and E stands for the concentrations at equilibrium. When you have a balanced chemical equation with coefficients, the rate at which, for example, the HI disappears is going to be twice the rate at which the H2 and the I2 appear because of that 2 in front of it. And because of that, the HI's concentration is going to change at a different rate as the I and the H. This is the type of problem which you probably could solve without using a Rice table. However, this is going to be much more useful later on. So we're going to use the same approach every single time. When we find out that the equilibrium concentration is going to be 0.100 minus 2x, and we set that equal to 0.078, we can solve for x and figure out how much the HI concentration dropped, and by extension, how much the H2 and the I2 concentrations grew. So that's here and here. Finally, when asked to solve for Kc, we simply write the equilibrium expression and plug in the values we now have solved at equilibrium. This top one is squared because we're using both the H2 and the I2, both of which are 0.001, and the bottom is squared because we square it in the equilibrium expression. And that is how you calculate Kc from concentration data.